Okay, so last time we were talking about how we can use the recursion tree to solve and find out the bounds with respect to recurrence relations, right? So for this one, for example, we had t of n equals to 2 times t of 2 t of n by 2 plus 1, and we know that in terms of the recursion tree, every level would have a different complexity. It was 1 for the first one, then it divides it into 2, and then we have 2 pairs of ones for the second one, then we have 4, so 1, 2, 4 all the way to theta of n, right? So the number of leaves. Now, just to remind
Sunday
everyone,
Kanta.
please, everyone, please mute their mic if you're not talking to me. There's a feedback. Okay, so if you remember that this part of your recurrence relation was how your algorithm divides your problem into separate components. In this case, as with the homework, I guess, is basically kind of like a binary tree where uh, you're dividing your problem into two halves, and you're trying to merge both of them together, and merging both of them together requires a complexity of 1, right? So so this was an example of an algorithm where the merging process requires constant time, while this was basically the time complexity for dividing your problem into 2. So if I look at our homework, I think the homework is a different thing, right? It's a big, okay. So for the third question of your homework, can someone tell me if this is true or not? Because is it going to be big O of log n? That is first thing. So anyway, so for the third question, you have to tell me whether the question is true or false. And if it is false, you have to tell me whether it is false. If it is true, you also have to tell me whether it's true or not, right? Okay, so this was the merging complexity for merging both of those parts together. So can someone tell me an algorithm which would have a complexity like this, where we would divide our problem into 2, and then merging those 2 problems just requires a constant time complexity? Some algorithm that we know.
Like a tree traversal?
Tree traversal, yes. I mean, but what would be the, yes, I mean, any with the, if we don't have any merging complexity, yes, that is going to be a tree traversal sort of. But any other popular algorithm that we know of, would binary search fulfill this particular time complexity? Yep, Revant is correct, right? A binary search would be, yes, Brian is correct. Binary search would not be 2tn by 2, it would be tn by 2, right? So what kind of, so let's see. What if I wanted to find the maximum number in an array by dividing the array into 2 halves every time? Would this be a time complexity for something like that? We are now talking about things that are the other way around, right? We already talked about how we can get an algorithm, and then we get the time complexity for this. But now I'm just in general asking, what type of algorithm would this time complexity have, like, look like? Yes, I would. So Brian, you're correct that I would have to search each of them. But what if I had an algorithm that divides my array into 2 every time until I have just the leaves, and then while merging them, I'm just returning the maximum of those 2 numbers?
Yep, a max would, because like that, because the 2t n over 2 plus 1 is basically, you're going to hit every single element of an array or tree, right?
Exactly. At some point, I would always hit every single element of my array. Now, let's say that I have an algorithm that looks like this. So let's say that FUNC that takes in an array, let's say ARR, and returns some form of an integer number, right? And this is just pseudo code, right, in C++ terms or whatever. And every time I'm going to cover the base case in a second. And then my divide case would be call the function with two halves of the array. So array 1, I'll call the first half of my array 1, and I'll call the second half of my array 2. And then let's say that these two function calls return a single integer, right? And let's say that it returns int A1 and int A2, right? And then the merge part would be if A1 greater than A2, then return A1, else return A2. The base case would be if size is 1, return element, right? So in this sort of an algorithm, what would this particular algorithm do? It would divide your array into two halves every time and return an integer A1 or A2. At the very base case where we have just a single leaf element, it returns that particular element. So the base case complexity is just 1. And then the merge case complexity is I'm just comparing two of those numbers, A1 and A2, and returning either A1 or A2. So would this get me the maximum number of my array? Would this be a recursive solution to get me the maximum number of my array?
Yeah.
Yep. And then would this have a type, what would the time complexity of this look like? We have T of n, and we are dividing it into 2 and calling both of them. So 2 n by 2, right? I'm calling both of them with two halves, and the merge complexity is 1. Am I right? Can everyone type in if they agree yes or they don't agree no? Right, so the reason I'm looking at this, so you guys agree. So the reason I'm looking at this particular algorithm is that we see that not every recursive formulation of an algorithm has a log n complexity, right? Even for this particular thing, 2t n by 2 plus 1, we have the time complexities of 1, 2, 4, dot, 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 and so on, all the way to theta n, where n is the number of elements. And we know that the total number of elements that are in this particular binary tree is going to be the sum of all the nodes, because that is for each merge operation, we have 1, and we basically have the sum of all our nodes, that is 1 plus 1 plus 1 and so on. And I have 1 plus 2 plus 4 plus 8 all the way for h levels. So we know that the number of nodes for a tree, depending on the height, is going to be 2 to the power of h minus 1, right? We discussed about this. In our case, h is going to be log of n. So 2 to the power of log 2 of n minus 1, but that doesn't really matter. So 2 to the power of log base 2n is, yes. So 2 to the power of log base 2n is n, right? Because log base 2n is essentially 2 to the power of x, that is going to be n, and this is x, so 2 to the power of x becomes xi. So this entire equation becomes n minus 1, that is theta of n. Okay, so that was your merging complexity and dividing complexity. So last time we were starting with merge sort algorithm. So here we have a merge sort algorithm that is three-way merge sort. So three-way merge sort essentially differs from a normal merge sort where we divide it into two halves. Here, three-way merge sort divides your array into three parts. Okay. Okay. So here we have our three-way merge sort where we are calling our function into three parts. So first we are calling from array 1 to n by 3. Then we are calling a of n by 3 plus 1 to 2n by 3. And we are calling 2n by 3 plus 1 to n. So we are calling it thrice. And then we are merging the first part with the second part array. So the first part, the first third of the sorted array and the second third of the sorted array. And then we have this entire merged array that is 1 to 2n by 3. And we are merging it again to 2n by 3 plus of 1 to n, right, to get the final sorted array. So can someone type out what the recurrence relation for this particular three-way merge sort would look like? So any ideas? Brian, is it so the divide part is correct that we are dividing it into three parts, but is it going to be plus of 2? Does merging require a constant time complexity of 1, or does merging require a time complexity of something else? Exactly, right. It is going to be 3t n by 3 plus of n. Similarly, we also have this unbalanced merge sort, that is we are now again dividing our array into 2, but we are only dividing the first third part of your array and the remaining 2/3 of your array, right? So in this case, we are just merging those two arrays, but this is sort of an unbalanced merge sort. Okay, so here we have, so in terms of recursion trees, we can solve these type of recurrence relations when we can sort of draw out the recursion tree and then figure out what the solutions are. So we have 3t n by 3 plus of n, that would be the three-way merge sort, right? Now, the unbalanced merge sort would be, I am dividing my first array into a third, so I have t n by 3. I'm then dividing the rest of my array into 2/3, so that is t 2n by 3, and then merging both of those parts together, and that is again big O of n. So we have this time complexity that would be similar to our unbalanced merge sort, right? Now, we also have some other examples for recursion trees. So we have 3t n by 4 plus of n. So 3t n by 4 would essentially be a case where we are dividing our array into 4 parts, but we are only working with 3 of them, right? So essentially think of it as I'm dividing my array into 4 quarters, and I'm only going to work with 3 of those quarters. And merging them together would be just an n complexity. Similar to this one, we also have 3t n by 4 plus of n squared, where n squared time complexity is the merge complexity, right? So it is not necessary that the number of parts that we divide our array, in this case 4, or in this case also 4, that we also need to call our functions every time for each of those parts. Does that make sense? So for example, let's say instead of us calling this function with, and this is just a random case again. So instead of us calling this array with halves of our array, we are actually going to call it up to the